So I'm David. My biggest idol is Richard Feynman. I'm always trying to get an intuition like he is.
My name is Lana. I'm a first year at the University of Waterloo and I'm studying mathematical physics.
Hey, I'm Anna. I'm currently in Vancouver and I'm in high school, grade 9.
I'm Dixon. I'm finished high school early, so that's really nice. My biggest idol is Elon Musk.
Yeah, I'm from Toronto, TCAS Toronto, and I'm really into quantum computing.
Hey, I'm Taman. Finished high school a little bit early, just taking that time to go through a little bit of higher math.
Okay, so first topic, proposition and predicates. We talked a little bit about this earlier, but yeah, so it's basically like probably the simplest concept, I guess, that you can think of when it comes to logic. Like a proposition is just something that is either true or false, like the most basic, like 0 or 1. And then a predicate just like sort of builds off of that. So it's like something that technically doesn't have a true or false value yet until we give the value to the variable. So like p of x, right? Like that is just like a predicate. It says like, oh, x is like a human or a rock or something. Like that statement doesn't have any meaning yet. It doesn't have a value of true or false. But once we quantify what x actually is, then it becomes a true or false statement. So to get a predicate into or to make a predicate into a proposition, we basically just have to quantify what the variables are. So if we do like for all x, p of x, that is now like a proposition. Yeah.
Mm-hmm. You can also get to, by the way, just as a meta comment here, we can all unmute ourselves and like feel free definitely to hop in. And the entire point is if you have something that you don't understand, ask it because you're being valuable to others by doing that. So anyways, what I was going to ask is it's also possible to turn a predicate into a proposition by actually just giving a value for x, right?
Mm-hmm. Yeah. Because then
Cool.
it's like because like we said, like, oh, if x a tree, if you say like, oh, let x be like a birch, then yeah, a birch is a tree. Yeah. But if you make like x a rock, so basically you're just turning it into a proposition by assigning like a quantifier. So by giving x like a meaning. Once we know what x is, you can like define whether or not it's true or false.
Are there any other ways of like trying to turn a predicate into a proposition?
From my understanding, it's just that you need to assign like a quantifier to the predicate, and then like, I mean, you just have to say what x is, and then so like for all x, or there exists an x, or just like x is equal to, but yeah. Anyone disagrees with that?
Wait, so if you have a proposition that's representing some certain predicate, that proposition is basically testing the validity of that predicate, would you say that's true? For example, if I'm saying that p of x equals a certain, like if p of x implies something, then if that whole thing is wrapped as a proposition, then is that proposition being like true? Is that testing the validity of the predicate?
Can you give me like an example?
Yeah, sure.
What do you mean?
So what he talked about in the lecture was like, let's say you have one predicate like p of x implies another like
p of x implies q of x.
Yeah, something like that. And then that whole whole implication itself is a proposition. And he said that if that proposition is like true, then that proposition being true basically means that that implication is true.
Are you sure?
But at the same time, it's like if you just have p of x implies q of x, that is still like, we still don't know what x is, right? So at that point, you still need to like be like, oh, for all of x, p of x implies q of x. Then it's a proposition.
I see.
But if you don't like know what x is, you can't like give it a true or false like value, right?
Yeah, David, what were you
saying?
saying?
You can like combine like a bunch of things. You can do like p of x and q of x, and like t of x implies whatever, like, but at the end of the day, that's still like a predicate, and it only like gets the true or false value until like when you give it like what value of x, right?
Well, I was under the impression that when you use things like imply or and or funny enough, that you're using those operations on propositions, but you can say something like p of x implies q of x.
But you need like a domain, right? Like you need to know what x is, right? Because like, I
see.
you know, because like at the same time, like you would have to be like for all x.
Yeah,
P of
that's
x implies
right.
Q of x.
So how about this? You can say something like R of x comma y is equal to P of x implies Q of x, because P of x implies Q of x is just a new predicate that you can then turn into a proposition by adding a quantifier like the A.
Yeah, like you always
cool.
like need the quantifier if you're dealing with predicates to turn it into a proposition, right? Because otherwise you don't know what x is, and then you can't be like it's true or false.
I guess it depends on your definition of what you mean by quantifying. Because if I was to say something like x is a birch tree and the predicate is x is a tree, does that count as quantification? Like, I guess it kind of does.
Yeah,
I
like
see.
quantification is just telling us what x is. So like for all of x, that just like it means that like P of x is always true. Then you can also be like there exists an x, or you can fully say like x equals 2. Like you just need to make sure you're declaring like what x is.
Cool. Because I'd always thought of it as being separate. Like if you were to say like x is a tree, like I always thought of that as being separate, as saying like for all x, P of x. But I guess, yeah, they're both quantifiers, because that's literally what quantifier means, like quantify. Okay, cool. Sick. Next up.
Are we all good on that? Any other questions? Okay.
I think we're good. Pavan, you're next.
Yeah, so I guess with truth tables, that's like the next step in predicates, where you can define the predicate in given scenarios of the propositions holding different values, and then all of a sudden you have a truth table. And from the way I see it, a tautology is a statement that's like 100% true. That's like, for example, if you have a proposition that's like P or not P, and then in that scenario, that when you wrap that into a proposition itself, that's like always true, right? And that's like what's cool about that is like we don't know what P is in that scenario, but we do know like that fact is always going to be true. So that's a tautology. And yeah, I found it really cool that he went into proofs, as in like proving some equation by the contradiction of that equation. Because from what I've heard already, I guess this is just from like my debate background, but like proof by contradiction doesn't carry that much weight. But like when I come here, I guess because it's binary, proof by contradiction is like just as good as like, that's like one of the best ways to prove. I don't think he mentioned any other way to prove a certain concept, but I found it fascinating that that proof by contradiction was such a powerful technique, because I guess in a binary domain, if you prove that it's not this, then it has to be that. I mean, like the opposite, right? But like, yeah, from my background, what I was thinking was that like, especially from my debate background, like there's so many different possibilities. If you say it's not this, it doesn't mean that it's that. So yeah, that's very interesting.
He does also bring up the intuitionist people, where they're like, oh, we don't accept proof by contradictions because it's not intuitive or something, which is interesting. Be cool to like purposefully, like what if you were in a class with a professor and you're just like, no, I refuse to accept your proof, because
that's literally like crazy. Like the whole thing is like, if one mathematician is like, I'm not convinced, like you have to be able to like break it down into these steps, right? Like
I feel that's a skill. I'd want to learn that skill.
To be like, I'm not convinced, or to be able to break a proof down into these steps.
To like challenge the professor, like just to see, like just to know that it's possible, and then to know how to do it, but then not to actually use it. But it's like, a tool to use. Like I don't.
Like that would be like a smart way of saying like, oh, I don't understand. Just be like, I'm not convinced.
Exactly. Oh yeah, just on the exam, I'm not convinced. Cool. Anyways, next up, Dixon.
Wait, just a quick question on that. What do you think is like? What do you think? Is there some utility in knowing, like, in being able to break it down?
What do you mean break it down?
Like being able to, like, as he says, access like the machine code of mathematics.
I see.
Because I find that like that's really cool. To me, that's just like so like that's so fascinating. just like being able to like creating such composite systems and like breaking it down like that, it's just cool by itself. But is there some utility in it as well? Because I don't see anything like from my perspective.
I think it's just like, because this is like the most pure, like I feel like mathematics can get, and you just need like a rigorous definition of what like a proof actually is. And I just think this is like the building blocks for that. Like, I don't know if like someone would write out a proof like this, like line for line, like no one would ever do that.
Yeah.
But it's just that like to be able to like do proofs like in a proper mathematics sense, like you need to have like a rigorous definition. And I think that's just what this is.
And it's also probably like a real proof would go into like millions of lines or something crazy. So I think it's just something
breaking down into like,
like for mathematicians to agree on something and to be like, okay, yes, that is a proof, that is valid.
Yeah.
All right, Dixon, you're up next.
Okay, I'll just run through all like the logic statements. So the negation is like not a function. So if it's true, turn to false, false, turn to true. And it's like basically how I see it is like if it's two trues, then like it outputs a true. Anything else is false. What else? Or is like if at least one of the statements must be true, anything else will be false. So basically, three of them will be true. One of them is false. Implication means that. Okay, so this one is like the double, basically a double arrow. Sorry, no, single arrow, and it's basically saying like saying that. How I see it, like the false section. I'll start with the false section first. It's kind of like a C0 function, where if the control qubit is 0, then it just doesn't matter. So it's always true. But for the other guy, then if it's true, if both of them must be true in order for it to be true, and then if one of them is true, if the first one is true but the other one's false, then it's false. And how I kind of see it is like implication is like if it's raining, then I will bring my I don't know, umbrella, right? So if both of them happen, then you fulfilled the statement. But if it's raining and you're not bringing the umbrella, that means you kind of falsified the thing because you're lying, right? And if it's not raining whatsoever, it doesn't matter if you bring the umbrella or not. So that's how I see implication. Nand is basically like it's like not and you can build any of the logical statements. That's higher order logical statements off the NAND function. So, yeah.
I was a little bit confused on this part because if you can build all of the like, so there's the unaries, which is like not, there's the binaries, which is like and or whatever, and then you can use NAND to build ternary whatever, all the future ones. But my question is like, why NAND specifically? Can't you just use some other random one? Like I have no idea on this answer. I think probably it's just NAND is the simplest one that you can use to build future ones.
Although, like, I don't think you can like build higher order operators from like not, just with not.
Yeah, you definitely need something binary.
But like, why this one? I don't know.
Yeah,
I'm told it has a little something to do with parity. So if you take a look at your if and only if, for example, or biconditional, I don't know how you call it here, you can see that you're always going to get two trues and two falses, right? So you'll never get something with an odd number of falses or an odd number of trues. So therefore, you can already, from that parity, see that you cannot achieve every single thing.
True.
So
but what about just a regular implication arrow?
Right. So there's something, I cannot remember the term, but you can prove by induction whether something can or cannot build every single connective, because you can prove if it can build every single possible binary connective, then it must be able to build every single trinary connective, and so on and so forth. So that's the inductive step. So the first step is just take that thing and make it build every single binary connective, or prove that there exists a binary connective it cannot create. And then by induction, it just falls.
Okay, cool.
Yeah, also one more thing for David, what you're saying, because I kept hearing that like NAND is universal, but I didn't really understand why. And the same thing goes for like C0 and like another gate, I forget what it is. They're also universal, or like the Toffoli. And I found out it's because like one NAND gate is like equivalent to like the wait, no, not one NAND gate. You have one NAND gate, and then if you take the output of that NAND gate and plug it into one and another NAND gate, then you have an AB. And if you have two NAND gates and you plug in those two outputs into another NAND gate, then you have A plus B. And there's like these few circuit configurations you can do. I'm looking at an image right now, actually. I'll send it when you have the Slack channel. But you can configure these NAND gates so that they're basically equivalent to AND. Like it's basically the same thing. So yeah.
So that's why it's just like a building, like a convenient building block, pretty much.
Yeah, it possesses like the heart of like not and AND. So that's a unary and a binary. So like since it has like elements of both, then you can like combine each other to represent both.
Teman, do you know if you had the NOR gate, if that one you'd be able to build up all future thingies?
Not sure, but I doubt it.
Okay. Guess AND is just really important. In any case, next up we have Anna. If you want to describe.
Okay, so universal and existential quantifiers. If my memory serves me right, I'm pretty sure universal quantifier, they're meaning like for all or for every for each, and then like etc. from going from there, and then existential quantifier like only for some, and then there exists or is like there is specifically one. So like basically if P of X, then Q of X is So does that make sense or?
What's the relationship between the existential and the universal quantifier?
I'm pretty. What was it? Actually, I don't remember that off the top of my head.
That's cool.
Yeah, that I don't remember. No.
Basically, like they're like the opposite, right? Because like if you have for every, or if you have like there exists, that does is like basically like the opposite of saying like for all.
True, because they you're only specifying one, while the other one specifies all of them.
They're like the negation of each other.
Yeah, I remember it. Oh, sorry.
Sorry, you can go.
I thought existential meant like there's just at least one, not only one. Or is that another one?
No, it means
That's
like,
correct.
yeah, there is at least one, but like that is like in this like logic, that is like the opposite of saying like for every, right? I mean, I guess it makes more sense to think about it like if you have for every, that's the opposite of like if you think about it from going from like for all to there exists, like you're going from every single X to just one X, but then like the same logic has to be applied like the other way.
But yeah, anyways. Cool. Next up, or Anna, if you want to describe logical equivalences, so the double-sided arrow.
Yeah, so basically the prepositions basically then are equal or like logically equivalent as they say it. So basically I always have the same truth value. So if, for example, P and Q were logically equivalent, then P is true whenever Q is true, so P equals Q or Q equals P. And if they're both false, then if one of them is false, then the other is false. And yeah, basically that means they're logically equivalent. I'm pretty sure.
What do you mean if one of them is false, the other one is? Okay, I see what you mean.
Yeah,
but then the statement as a whole is true still. If one of them is false, the other one's okay. I see.
Yeah.
Wait, would it be correct to call it the tautology operator? Because essentially, for the double-sided arrow to be true, the statement as a whole has to be a tautology.
Yes, it does. So.
But like, because.
Oh, it's not? Okay.
Right. Well, a double-sided arrow, there's a statement on the left side and a statement on the right side, right? We're not saying that they both have to be true. We're just saying they have to match.
Yeah. That's right.
So
and the resulting proposition, like when you take the thing as a whole, that's a tautology, basically.
But not always, because like,
not always.
It's not
a
true
they're different
statement. Yeah, because like a tautology is like true independent of like what is given, right? Like P and not P, that'll always be true independent of what P is. But I don't think like an if and only if statement will be
You're right,
true independent of like the given predicates.
So it's like only half a tautology operator.
I don't know if I would like describe it using like tautologies, but
okay.
Yeah.
All right. Taman, you're next on, or unless Pavan, it looks like you have something to say.
No.
Or
why do you think that?
Oh, sorry, you're just unmuted. Sorry. Okay, whatever. Temen, you can go next.
All right, let's see. We have order of quantifiers. Not much to say here except they matter very much. For all something, there exists something is very different from there exists something such that for all something. In one case, you're implying that a certain condition holds because there exists one thing for every other thing that you choose. Whereas in the other case, you're saying for this one thing, it holds for every single other thing. Now, an axiomatic system, I'm not sure which definition we want to go for since it's pure logic. So an axiomatic system, also called sometimes a deduction system, is a syntactic system in which you can manipulate things according to certain rules. For example, in logic, your deductive system would be given A and B. If I have the statement A and B and I tell you that A and B is a true statement, then you can tell me, you can derive from that A is true, or you can derive from that B is true, because they both have to be true for A and B to be true, right? So for example, that rule you would call conjunction elimination, because you took A and B, the and is your conjunction operator, and you just deleted it because you went from A and B to just A, or you went from A and B to just B. So your axiomatic system or your deduction system is your list of such rules from which you can manipulate things. Think of it like an algebra system, but for logic, right? And now from this, you have formal proofs. So if I give you one statement and I say this statement is true, then I tell you to prove this statement, then you use your axiomatic system, which is your set of rules or algebraic manipulations possible to get from this statement to this statement. And that creates what you call a formal proof.
Do you want to give the ATM? That's the one that I'm familiar with axioms, tautology, and modus ponens. And that's what a proof is. I'm sure there's probably many definitions.
Yeah, I mean, like at the end of the day, it is like a finite sequence of propositions, right? But like you can pull that from like the list of axioms, which is like the rules that you set in like whatever space, right? The things that we've set to be true, or the tautologies, or the I don't really know how to read Latin.
Yeah, neither.
You know, like that too. Before, like if you and them, it'll lead you to the current proposition that you're on. But yeah, at the end of the day, it's just like a sequence of propositions.
I think the definition that I provided there was very much influenced by the final point, which is consistency and importantly, completeness, because it is necessary to have a logical or a natural deduction system, which is your set of rules in order to prove the completeness theorem. But that is.
I try explaining that.
Yes, go for it.
Okay. So my understanding of consistency, completeness. I think I'm actually thinking consistent. My definition of consistency, or the official one, is kind of weird, which is that you can, or there is a proposition that's false. That's the definition for a specific axiomatic system to be consistent.
I don't think it's that it's false. I just think it means that there's something that you can't prove with it.
Oh.
But that means that like you can't assign a true or false value to it, right? Because if you could prove that it's false, that's still proving that it's false, right?
That there's something. Okay, you're right. Yeah. And the reason that is a really sweet definition for consistency is because it's really short definition. And in practice, when you develop that definition, it ends up being like a full definition. Basically, what happens is that if you can prove, or I should clarify, suppose you had some axioms, like you're listing off some rules of the world you're creating, like the little world here, and you had P and then not P. In that case, what you could do if you were like really nefarious is you could say P and not P, and then you'd have a statement that's completely false that you could add to your list of statements that you're allowed to use. And then you could use that falsehood, you could use the implication arrow, and you could prove whatever you want. Like literally whatever you want. Every single statement in the system could be proved, which would break the definition that we came up with. It's kind of like a roundabout way of saying that something is consistent, but that's the way that I end up understanding on why something's consistent. Yeah, you can't prove false.
It's a little
Yeah.
mind-boggling because at the same time you're thinking like, well, then that there can't be like a set of axioms that proves everything, you know? And like, how do you think about it from that perspective? Like, and how do you show that you can't prove something using a set of axioms?
Yeah, that's the Gödel point.
Yeah, wait,
Yeah.
one sec. What did he mean by like a system, an axiomatic system where a proof is right when you can arrive at that final statement without the use of any axioms within the axiomatic system that you use to arrive at that final statement?
Are you talking about propositional, like the axioms of propositional logic?
No, at one point, I don't think so. At one point, he was talking about how you arrive at like you do your proof and you arrive at the final statement, and to like Tom said, to arrive at that, you use the axioms within your axiomatic system, right?
Okay.
Those are like what you can play around with. But he said that a certain like you can to truly prove it, if you can arrive at the final statement without the use of any axioms within the axiomatic system, then that's like truly consistent. Is that like, yeah, poke holes on that.
Oh, I guess it, okay. I guess it's like saying that, like if you can prove that statement without using any of those axioms, that means that like there's something that those axioms can't prove.
Yeah, what does that mean? I didn't get that.
So
Really?
like, say you have like a set of rules, right, that you're allowed to like use. Like for us, it would be like a 1 + 1 = 2 or something like that. Like you have those rules of mathematics within your like system. This is what we're like agreeing on that is like completely true. But if you can prove some statement without using a single one of those rules, that means that that system is consistent because there's something that that system can't prove.
Yeah, but like, how do we come up with something else? Because like, what the axioms we have right now, aren't they like collectively exhausted? Like,
I mean, there's different sets of rules for different like sets, right? I guess they dive deeper into that later. Like you can't like translate logic from every like set of numbers into another set of numbers. I mean, there are things that like agree within like spaces, but I don't think every single one has the same set of rules. But
so just a quick comment on that from the perspective of modern mathematics. Currently, we're using an axiomatic system called ZFC, or Zermelo-Fraenkel choice axioms. So there are a list of axioms now. Axiom of choice used to be debated. People accept it now, it's fine. But there are certain theorems, well, propositions that are not proven yet. One of them is the continuum hypothesis.
Yeah, that's right.
Without getting too much into what that is, some mathematicians use ZFC, rejecting continuum hypothesis. Some mathematicians use ZFC with continuum hypothesis, and both systems are consistent as far as we know. So that statement has been proven to be outside the bounds of ZFC. So
can I clarify something?
Yeah, go for it.
Yeah. So, and you can tell me if I'm wrong here, but from what I understand, essentially what happens is by some complicated process, you can prove that something is not possible to prove. And in that case, if you really want that thing to be true, you can just add it to your list of axioms.
Yeah, that's basically what Gödel's entire work,
Yeah. And so that's why when you're saying, oh, mathematicians are debating whether to add the consistency or not, basically you're saying that we know that it's impossible to prove this, but we'll just add it to the list of axioms and boom, there you go, it's proved.
It's more so like in some cases it might be useful or intuitive. In some cases it might not be, and you can choose to use it or not. And until we arrive at a point where there arises a contradiction in one of the two systems, we have no clue. Because, for example, if you take your axiom of choice, right? Like people accept it nowadays because it's incredibly useful.
Pause. Just a second. So since most people here don't know what the axioms, like axioms is next lesson. And at the cost of entertainment value, I don't want to dive into it because it's boring. It is boring. For me, it's fun to listen to because I know what it is, right? But for most people here, it's boring. But as we get to that level later on, then we can talk about that.
Yeah, apologies for that.
That's all
I think the point is just without getting
Dixon,
into
yeah?
yeah, sorry.
No, it's Van go first.
Yeah, so without getting into axiom of choice is just imagine I'm saying like garble of strings. So axiom choice has many different consequences, right? Like from this magical thing, there are many other magical things that arise from it. One of those magical things happens to be something called Zorn's lemma. This thing, super useful. That's why we like axiom of choice. But another magical thing that comes from axiom of choice is Tarski paradox. It's mind-boggling. Essentially, you can take one sphere and you can make it into two spheres. Like you can duplicate objects. It's very not nice, but if we accept axiom of choice, we have to accept this too. So there's good and bad that come with it, but we have decided collectively that the good much outweigh the bad.
Okay. Well, I'm sure we'll reach that eventually in this series of lessons. But yeah. Dixon, you were going to say something?
I was just wondering, like, would it be possible that there's something outside our realm of mathematics that we cannot prove that, or like that we cannot see, but if we changed our axioms that we would be able to like deduce that? Like, what is that possible? Let's just say like a faster than light travel. Let's just say that's something that we can't prove within our current system, and then, but we can prove with using another axiom choice. So is that possible, or is that or our axioms like fundamental?
Can you say, I think you'd be, well, the thing is you get to choose the axiom. So let's say you wanted some crazy thing to be true. You could just create a world where one of that crazy things is an axiom. But the consequence is that that world might not be consistent, where basically, you know, if two things oppose each other, you can prove whatever you want, and then everything is meaningless. So it's kind of like, you could create a world like that, but I guess it becomes about applicability and how useful it is to create a world like that.
So I'm really glad you brought that up, because over the past like a decade or 2 decades, there's been a new field of mathematics. It's very new right now. It's called homotopy type theory. And essentially, so logic is one foundation of mathematics, right? And we're doing propositional logic, I guess predicate logic, but you can also have like IPL or intuitive propositional logic. Essentially, there's a lot of systems. Homotopy type theory is trying to establish itself as another system. And the cool thing about this, to my understanding, is there are no axioms.
Oh, okay, huh? So it's like a pure objective.
I wouldn't say so, but it deals a lot with types. So it's very much into the computer science realm. And now I cannot speak on the matter because there's one book on the subject, and this book has nightly builds, as in people are actively editing this book
That's funny.
as they discover more of the subject. So it's like a book with its own GitHub repository. That's pretty cool. It's a 500-page book. I'm only 30 pages in, so I can't say anything on the topic, but it's pretty cool.
Well, cool. Yeah, no, that sounds really interesting.